Welcome to today's demo about imaging 2D materials. I guess today we're just going to do a little demo of the FlexAFM, and I'm going to put a sample under a 2D material, and then we're going to just image it. Simple as that. Just a little background about our company, Nanosurf. We've been around since 1997. We started in, we're a Swiss company. We're global. We have offices all over the world, and we're a full range provider of AFMs and STMs. We're known for building systems for research, education, and for industry. We build very modular, compact, easy to use systems, and they're all well known for having high Swiss quality. As I mentioned, we do AFMs. We build AFMs for industry, such as the flex mount in the left-hand corner. Oops, why didn't that work? Flex mount. The core AFM, which is one of our newer AFMs, is a tabletop research grade AFM, and P6, which you might hear more about in the coming months. So this demo is going to involve 2D materials, the measurement of 2D materials. So in about 2007, some researchers out of the UK discovered that if they took Scotch tape and put it on a piece of graphene, they can peel off really thin pieces of carbon. And what they found was that these layers were about 1 atom thick. And so these are the world's thinnest materials, and they have huge aspect ratios. So this might be maybe 10 microns from length to length, but only about 1 nanometer thick. So the ratio of area to height is extreme there. And this research, I mean, this was published 2007. 2010, they got the Nobel Prize for the work they did there. So research into 2D materials has been growing exponentially. This data is a little bit out of date, but so I don't know, we can maybe picture that it's 2009, 2020, we're all the way up here. So it's more and more research on all materials. Definitely graphene is probably the most popular now. There's lots of basic research in scientific institutions and in universities and in industry also. There's some interest. Here's like for flexible electronics. So who is in the 2D materials community? Well, the 2D materials can be a semiconductor, a conductor or metal, or an insulator. So any of those industries, so basically everything. So really what you want to find what you want to learn about the info that you want to know about a 2D material is maybe the thickness is probably the most important. So a 2D material has to be single layer of graphene or another molecule. And so understanding if it's single or multi-layer is important. Understanding maybe doping profiles. So if you carbon, if you have another atom or another element within that, you want to know how it's distributed. Conductivity. 2D materials have lots of properties, interesting properties of different conductivity, different thermal properties, and maybe work function. So this is how much stored charge or the surface potential of the material. So in general, as I mentioned, a 2D material it has a huge aspect ratio. And so essentially it's completely a surface. And so the surface is the device here, and AFM is the perfect tool to characterize surfaces. So let's get into some examples, some AFM images. So here's an 8x8 micron AFM topography image, which is overlaid by a KPFM image. So this is a Kelvin probe force microscopy channel. So the coloring is the KPFM signal over a topography in 3D. And if you stay tuned for a week or two, we'll have another demo that involves KPFM. So if you want to learn how to do KPFM, we'll have another demo with that technique. Now, if we look at this edge here, and we just look at the line cut across it, we can see that it's about 15 or 16 nanometers in thickness there. So this isn't a single layer of graphene. So this is a multi-layer piece. But if we take a look at the KPFM signal, remember this, the color above the contrast that we see there in the color, and we take a look at this square I've outlined here, we notice there's some contrast change here. And now if we just look at topography there, which is highlighted here in the corner, and draw a line across that, we see that this piece has a thickness of about 0.4 to 0.5 nanometers, so 4 angstrom in thickness. So this is actually a single layer of graphene above this multi-layer piece. So we can exfoliate this this single layer on the top, and then we have single layer graphene there. Let's go to another example. This is MOS2. This is an 18.5 by 18.5 image. This on edge is probably around 15 microns, notice. Now if you take this is just topography, if you take a line cut across the edge of this crystal, you find that the height across of it is about 0.6 nanometers. So again, this is a single layer of graphene or single layer of MOS2 with 0.6 nanometer thickness. MOS2 is important in optoelectronics, so it has a really high efficiency of light to electric signal, using a lot of electrical transducers. Here is another example of pyrene. Now, pyrene isn't a traditional 2D material. The reason is the molecule is actually quite large, but you can make large sheets out of it. And this is about 10 microns across from edge to edge with a thickness, if you just look at topography across the edge, of around 1.6 to 1.7 nanometers. So it has about a 10,000 to 1 aspect ratio there. So while it's not a traditional 2D material, it can definitely be considered that it has a considered one just because of its huge aspect ratio. Here's the same sample, pyrene, or same type of material. And this time it's a self-assembled material, and so it grows in sheets, but then these sheets can actually grow secondary layers. So now we see here, if we just take a histogram of the AFM image here, the topography, we here at 0, we have the silicon in the background, and then we have 1, 2, 3 different layers of these pyrene sheets. So in today's demo, I'm going to be highlighting the FlexAxiom. So it features a high resolution flexure scanner, so very flat scanning. That's ideal for these really flat materials. It's features low measurement noise, so under 40 picometers of measurement noise, and this is what you need for, as I showed you before, we're looking for layers that are 400 or 600 picometers in thickness. So we definitely want to be below that in noise. And also we can do some advanced electrical modes like KPFM, which I showed an example of, or thermal modes. So we can do scanning thermal microscopy. We have a 24-bit controller that allows you to get well below the digitation depth, I guess, of the ACD. And it's very modular, so it lets you add accessories to the system to look at different properties, magnetic properties, thermal, as I just mentioned. We can also even do things in liquid if you wanted to. So another nice thing about the Flex is that it's glove box ready. So because it's modular, we can take all the pieces apart. They easily fit into a load lock, as you see here, a load lock on the side. It's very compact. Again, it can fit in this load lock. You can take it in and out of the glove box, no problem. We can also configure it with a motorized stage. This allows you to move the sample around under the tip from outside of the glove box. So you can do it from a joystick or from software. Also lets you do batch processing. So you don't have to keep on sticking your hands into the glove box to move the sample around. You can do everything from outside. And we also feature this self-aligning cantilever holder. So when you change the cantilever and put the cantilever holder back on, the laser is going to be aligned to the cantilever already. You don't have to fiddle around with that at all. So just to kind of step back a little bit and just talk a little bit about how an AFM works. So the basic detector of an AFM is the cantilever and the tip. So what you have is a chip the silicon chip. At the end of the chip, there's a long cantilever. I mean, this is maybe 200 to 400 microns in length. And at the end of that is a sharp tip. And this is what we're going to do to probe the surface. Now, to detect this, we take a laser, we bounce a laser off the end of the cantilever, and it bounces and deflects off that and hits a detector. So when we push the cantilever, or the tip against the surface, you can see that the cantilever actually bends a little bit. That causes the laser to actually deflect. So this deflection is what we're going to detect electronically. And from that, we can detect forces, we can detect topography, height, or any secondary modes like KPFM signals, all from this laser deflecting off the laser in the deflection. So let's take a look at actually how the force on the actual cantilever. So the overall force is made up of two actual forces. One is the restorative force of the cantilever. So the cantilever is just a spring. So this is a spring constant on a cantilever. And the secondary force, which is the force between the tip and the surface. So we call this a tip sample force, or tip sample spring constant. Now, when we're far away from the surface, KTS is actually very close to zero. So this graph right here is a plot of the force, not necessarily the spring constant, but the force as a function of the tip surface distance. So as we go toward the surface, which is to the left here, we'll feel an attractive force pulling it downward, pulling it toward the surface. And as we get really close, we start to feel a repulsive force. So this is a positive force against the surface. Okay? So attractive toward the surface, and it turns around and becomes a repulsive force as we push into the surface. But so that was what happens in contact mode imaging, or static mode imaging. But what we're going to demo today is what's called dynamic mode or tapping mode imaging. And the difference here is that now we have the same chip or the same cantilever, and at the base of the cantilever we attach this shaker piezo. And that shaker we excite with a sine wave, with a voltage in a sine pattern, which causes the shaker to shake, the piezo to shake, and which causes the cantilever now to oscillate. Now this laser that's bouncing off the end of the cantilever, instead of being static and not moving, it will hit the detector and actually start to move back and forth across the detector. Now, so the signal we get from the detector now is also a sine. It's going to match what we get in excitation. It might vary by some phase difference, but they look the same. So this is what we call dynamic mode or tapping mode. And so let's take a look at how the force is in dynamic mode. So it's the same equation, but now instead of a single point along this curve, now we're oscillating across at this point right here at a certain height above it. So if we're oscillating a certain height and we're in this attractive regime where all the forces are less than zero, then we're in what is called attractive mode. Okay, so all the average of all the forces there is less than zero, so it's attractive. This is a stable imaging mode. Now, what happens if we push into the surface a little bit harder? So we go further into the surface. Well, what happens is that instead of now all the forces being less than zero, now the average of all the forces now, if we're oscillating here on this side of the curve, is greater than zero. So now this is what we call repulsive mode imaging. Another name for repulsive mode imaging is tapping mode, because in tapping mode, on every oscillation, you tap the surface. You hit the surface every single time. This is also a stable imaging mode. So we can image stably in attractive mode or repulsive mode, right? And the height. So if you notice the average, so we're oscillating across a single point here, the mean height above the surface is going to be a little bit different. So in attractive mode, you're actually a little higher above the surface. Because you're not touching the surface, sometimes this is referred to as non-contact imaging. So we're detecting kind of the gradient of the force. We're not actually feeling the surface at all, but we can still image the force that way. In repulsive mode, we're much closer to the surface, so there's a difference in a couple nanometers, or maybe even less, between repulsive mode imaging and attractive mode imaging. So now let's talk about maybe, because in an AFM, in our system, we're not detecting actual force, but we're detecting either a shift in frequency, and actually in our case, we're detecting a shift in amplitude. So the resonance frequency of a cantilever actually also depends on this tip surface interaction force. So if we're imaging again in attractive mode, remember we're here right in this attractive regime. The frequency, which is given by this orange plot, so the y-axis obviously is denoting both the force and the frequency, but the shape is about the same. So if the as we oscillate in this zone here, as the tip surface interaction force decreases, the frequency will also decrease. So the frequency decreases this way, right? Now this is attractive mode imaging. Force decreases, frequency decreases. Now in repulsive mode, the opposite happens. So if we're in repulsive mode, we have a increase in the force that leads to an increase in the frequency. So these are the difference: decrease in force, decrease in frequency, increase in force, increase in frequency. But what would happen if we're in attractive mode? So we're imaging on this attractive regime here, and we encounter a repulsive force. Okay, so as we're scanning over the surface, we could the force, the tip surface interaction force can change across the surface if there's different materials there. So just a reminder, as the force decreases in attractive mode, the frequency decreases. Now, what can happen though is if you encounter a repulsive force, if we're in the attractive regime, and we encounter a repulsive force, what can happen? Well, the frequency, as the tip surface interaction force decreases, the force actually, or the frequency actually increases, as you see here. So this is what's referred to as a mode hop. So we're imaging what we think is an attractive mode. We encounter a repulsive force, but the frequency increases. So this is more kind of abstract because we actually don't detect force. And let me show you what happens when we actually look at the amplitude and the frequency. So let's start with attractive mode. Remember, attractive mode, the force is less than 0. If you were very far from the surface, it's given by, remember, there's no force, the tip surface interaction force is 0. As the force starts to decrease, we'll get a shift in the resonance frequency that becomes more negative, right? So it decreases in the resonance frequency. In repulsive mode, it's the opposite. So as we start with 0, as we get closer to the surface in repulsive mode, the frequency starts to increase, okay? Now, the interesting thing happens with this when we're in attractive mode and we encounter a force that's greater than 0. So in attractive mode, what we expect is all the forces to go to the left, to become smaller. But when we get a repulsive force, this causes the frequency now to shift all the way to the right. And what can happen is that we shift over to the other side of this Lorentzian, or whatever you want to call it. So now we're actually at a new stable height, which is, if you notice that these overlap at the same exact point. So we're at a new stable height in not attractive mode, but in repulsive mode. And if you remember what I said before, in attractive mode and repulsive mode, we're imaging at different heights above the surface. So this can cause a difference in height in your sample. You can measure the wrong height maybe, but also can do line glitches and things like that, or some sort of artifact in your imaging, which just at that certain line or a certain point. So that's what we want to avoid. So how do we avoid this? Oh yeah, so here's the animation, it shifts to the right, stabilizes at a new height. So how do we avoid this? Well, in attractive mode, or when you're imaging 2D materials, as you pass over 2D materials, the tip surface interaction force may increase, okay? If there's a large change in the tip surface interaction in attractive mode, this leads to a mode hop, okay? And this mode hops into the repulsive mode. So when you're in a mode hop, it leads to a new stable imaging height. So now the heights are where you were before is different from where you started, or where you are now is different from where you started. And that means that any sort of height measurement you want to take, now remember in 2D materials, one of the parameters that's really important to know is the height of these samples, and that will be wrong. So how do we get around that? Well, if you always image in repulsive mode, then you'll never have this mode hop. And so there'll be no change in the stable imaging height. So that's what I'm going to show you how to do is how to set up the FlexAFM to image in repulsive mode. And I'm going to set up, put in a 2D material sample, an MOS2, and I'm going to start imaging that. So here is the sample we're going to look at. Here's an optical image, optical micrograph of it. It's just these triangular crystals on the surface, a piece of silicon. I'll go through these steps. I'll place the sample. I'll mount a cantilever holder. I'll show you how to select the cantilever and do a little basic laser alignment. Then I'll show you how to set the frequency, the measurement frequency, and to set that to repulsive mode imaging. Then we'll approach the sample and then actually start imaging. And while it's imaging, we'll have time to take on questions. And I guess Saju mentioned that we shouldn't use the Zoom chat, but use the Q&A button. Or you can email us at info@nanosurf.com if we don't get to your question, or if you want to ask a more complicated question that maybe we can't answer on this demo. So let's go ahead and let me switch screens now to, okay. So there is our flex axiom. And let me just zoom out a little bit. So back up the camera so we can see there's a controller. That's where I was sitting. And here is our system. So I will first mount a cantilever. So I've already have one mounted on the in the cantilever holder. To do this, I just lift the scan head, place the cantilever holder on like that. That's all we have to do. Now the sample is the silicon chip. It has the CVD grown MOS2 on top of it. It's then glued or stuck to a metal disc, and then this sample holder had these little magnets to hold it in place. So I'm actually going to clip it too, just to make sure it doesn't move. Oh, it's stuck. Okay. It was placed onto the, we're using a micrometer stage here, not the motorized stage. And then, okay. Now the next step is we select the mode and the cantilever. So here in mode, I'm going to switch to phase contrast. Then with the cantilever, what I have mounted here is an ACLA cantilever by App Nano. This is a stiff tapping mode cantilever, so about 40 newtons per meter, but we can measure that in a second. Okay, first, as soon as I mount a cantilever, I want to first check to make sure that the cantilever is there, you know. So here is a top-down view of the cantilever itself. Below, what we see is a side view of the camera looking at, or of the cantilever looking at about a 50-degree angle. So first step is to check the laser alignment. So this button here, I notice that I have a good sum signal. This is the detector intensity at the top, and the laser is the deflection from the laser is near the center of the quad detector here. Now I can, as long as it's inside this square, I can image with this, no problem. if I really wanted to be super careful, I guess, about it, I can also try to move the laser to the middle, but in reality, I don't have to do this step. So in order to move that final step, all I have to do is remove the camera, and I'll center it in Y first. And an X next. That's all I have to do with that. And again, that was completely optional, really. All right, let me close this down or make it a little smaller. Now I want to take a look at the resonance frequency of the cantilever. To do that, I go to the frequency sweep button. And easiest way is just to click the button here, find vibration frequency. Now what it does is first it does a very coarse sweep over a very large range. It looks for the largest amplitude at all frequencies. It finds the largest amplitude and then zooms in on it. And now what it's done is done a final fine sweep where it's only taken a small range. This is a 2 kilohertz frequency sweep and found the amplitude, the natural resonance frequency and amplitude of this cantilever. Now, if you notice, I am to the right of this frequency. Now, when in my my talk before, I was telling you that that's repulsive or that's attractive mode imaging, okay? And now what we want to do is actually switch to repulsive mode. So we want to be actually on the left-hand side of this peak. Now, the easiest way to do that is to go to this fine vibration frequency, the arrow there, click on the down arrow and click configure. Now uncheck this box that says use upper sideband. I want to uncheck that, press OK, and now try to find vibration frequency again. The other thing that the software does for you is it sets the free vibration amplitude automatically, or sets the excitation amplitude automatically based on your free vibration amplitude. So this is how the actual amplitude of the cantilever, right? In volts. So this is what we measure off the detector. For these measurements, so the larger the amplitude, the larger the number here, the bigger the amplitude of the cantilever. Now, because we're going to be measuring really, really thin surfaces, we want to actually have a smaller amplitude. We can't really measure a thin surface with a huge amplitude. So I'll show you how to do that right when you start imaging, actually. So all we need to do now is press OK. Now, the cantilever is all set to go. So what I want to do now is move the sample into position. First, I have to be able to see the sample. So I'm going to start with a coarse approach. So with the advanced button here, click and hold. Now you can start to see the surface appear in, let me zoom in once. Okay, so that's probably close enough for now. Now what I want to do is now actually find a nice region of interest on the sample. And let me zoom in on this scan too. Now these little blue, let me focus down. Yeah, you can start to see the little blue triangles here. These are your MOS2 samples. Now I'm just gonna, really be nice to image a single one out by the edge, but I think you get a little bit more, it's a little more interesting maybe when it starts to get a little thicker here. So I'm gonna pick this location right here. Now, next step is if you look at the side view there, you can start to see the laser position right below the cantilever. So I'm actually fairly close. So at this point right here, I can either maybe try to approach a little bit more, or I can actually do an automatic approach. So I'm going to do that. While that's doing, I'm going to just close this acoustic enclosure, so we don't really need to adjust the sample anymore. And I'll just close that. So here you can see the cantilever and the surface starting to converge. So you see basically the laser spot right here and the reflection of the laser spot on the surface, and those two are converging. And when they do converge, you'll get an approach done dialog here. Okay, so let's start imaging. Let's start with maybe a 25 micron image. And let's start with these values here. Okay, so first thing I notice is that the sample is actually tilted relative to the orientation of the scan head. The scan is on a tripod, so we can adjust the angle relative to the sample. It's almost impossible to get the sample actually completely flat too. I mean, there's different thicknesses of glue and things like that when you're attaching it. So what I want to do is actually fix this angle. And what I can do is I can do that through software. So if I go to the More button here, and on the first screen, which is imaging, I have this little button that says adjust slope. So let me just click on that. Now we'll restart and notice that it's now more centered, I suppose, or more not as tilted. Okay. Now, what I want to do now maybe is let's try to increase some of these gain values. So I want to get the forward and backwards curves matching up. And I think what I want to do also is maybe decrease the free vibration amplitude. Remember, I mentioned before that this is a fairly large amplitude, and we're looking at really, really thin materials. So I'm going to go down to 250 millivolts for that. Yep, and now we can see the phase is actually giving us a nice, better contrast than before. So I think we're going to get a nice image. So let me just start this scan over, and that's it. And we'll just wait till we get an image. I guess I can take some questions now, Saju, if there are any.
Yeah, so I think one of the big questions that came up was the MOS2 image that you showed in your presentation had a lot of spikes on the edges of the material.
Yeah.
Can you comment on that? What could that be, or is it real, or is it?
I see it in this particular sample. I see it all the time. I'm not sure what that is.
Okay.
What we could do is image in contact mode, and if it's a large kind of electrostatic force or something like that, it would we get rid of that. So that was one way of doing it.
Okay. So another question. Sometimes artifacts also appear triangle. How do you confirm that a sample and not an artifact of a specific shape, I guess, instead of just triangle?
Oh,
I think this is more of a generic imaging question than specific.
Oh, okay. Yeah, I mean, a lot of times you see in a phase, you'll see actually a jump. So the contrast at a certain line or something, it'll just switch. And let me show. I might have some examples of that. Let's look at this. So here's another same kind of image, and you notice that when the phase, so the phase channel here, it starts to get, it changes really at one point halfway through, and then the height here also changes, if you notice that. So this is an artifact, imaging artifact. that because the phase changed, it went from something really clean and then it became really jumpy. And now we're starting to see these changes in height in this image.
Okay. I hope that answered the question. But another question was, what is the meaning of P gain, I gain, and D gain in context of an AFM?
Right. Okay. So the controller there, and here you can actually see an imaging artifact. It just jumped right there, that line. The controller uses, so in control theory, you have a PID loop. The P stands for proportional, I is integral, and D is your derivative. And it basically means when you with an AFM, you have an input signal, which is, in this case, it's the amplitude of the cantilever. And you compare that to the set point that you've set right here. So we're operating at 50% of the free air amplitude. And so you create an error signal between the two. And then you can do one of three things with that error signal. You can multiply it by a constant. You can basically take the integral or the area under the in time, and then and multiply it by a constant, or you can take the slope of that line in time and multiply it by a constant. And so those three things, multiplying by a constant proportionally, or by the integral, this is the integral gain, or by the D gain. So in AFM, integral gain really is the most important parameter there. It means that we look at the signal and we look at it over a small time period, and then we multiply by a number and then use that to control the feedback of the system. Now in this image, what I can do is I can, let's try to decrease the I gain to something that's going to be way too low. So I'm going to decrease it to something like 100. And what you might start to see is that in this second channel, which is amplitude, more signal is starting to appear. So there's more contrast in the amplitude signal. This is my error channel. So this is the difference between what my actual signal is and what my set point is. So if I see any contrast in this image, that means my gains are too low. Now, if we go over to the actual imaging signal, notice that it looks kind of, I don't know, out of focus, I guess is the right word. I don't know if that is. It's blurry, right? So there's almost no contrast in this image, and almost all of it is an amplitude signal. That means that my I gain is too low. So let's go now in the opposite direction. Let's say we put too much gain. Let's go to something, I don't know, 6,000. Oh, yeah, that works. So now what's happening is that the controller, this number that we're multiplying by the error signal, is sending a signal back to the piezo, which is too strong, let's say. And what can start to happen is now we start to get these oscillations, these resonances. And now if you look at the amplitude signal, it's gross, right? It's nasty. And then this Z-axis signal is also, there's a lot of noise in that. So you have to find a happy medium between too much gain and too little gain. And between about 1,000 and 2,500 or 3,000 for the flex is about, it's about perfect.
Thanks, Ed. So I think we have some really active participants here. To your previous answer, one of the participants answered that if you rotate the scan angle, and then if your data if the data also rotates, then it's a sample. Right? If it is not, then you know it's an artifact. This is a question of how do you distinguish between an artifact and, so this is from one of the participants, and thank you. And there are a couple of other people who also answered for the thin spikes on the thin film, saying it could be dust particles or something similar. So again, thank you for those answers. The next question really, so what's the difference between an electron microscope and an AFM? Why should I prefer an AFM to an SEM? So let me take this. So we had a webinar last week, pretty much addressing exactly this question. Why AFM, what instrument do you choose to analyze your samples? So I would request that, and that's available right now. A recording of that is available on our website. So please watch that. The answer here is going to be just too long to address that question here.
Yeah, I mean, the sample prep, I mean, for SEM, I would have to do something to the sample and then pump it down. If you noticed, I just put the sample under the AFM and started imaging. And within a couple minutes, we have already an answer.
Okay. Another question, how to get rid of drag in the image while analyzing the sample? Is this more post-processing answer, Ed?
Oh, it could be, yeah, drag. Is that, I'm not sure what that refers to. Maybe streaks, possibly, in the sample. So yeah, if there's streaks, we have two things. I mean, depends on what the streak is from. So if you have a streak because you did a mode hop, you can do that post-processing, and there's software out there that will find the streaks, so find the spikes in the line, and then basically subtract it and then kind of interpolate between the lines that are around it to give you a nicer looking image. Our controller, also our ISO stage, if you have a kind of environmental noise, so let's say something, I don't know, there was a large crash outside, right? And then that caused a big bump, a jump in the signal, so a big bump. Our controller, our ISO stage and controller talk to one another. And if they detect that, it will tell the controller to rescan that line that there was a big streak on. So one you can do in post-processing, and one our controller tries to do while it's happening.
Okay. This question, can we do a demo with a DNA sample? Answer is yes. We'll try and schedule that soon. We cannot do one today. Just don't have the samples ready. So that's going to take some time. We'll schedule one and we'll let you know. Next one, in your AFM, while putting the sample, how will you make sure the sample thickness is compatible?
So when I'm placing the sample, when I'm placing the scan head over the sample, I take a look underneath and make sure it doesn't crash as I bring the scan head down. Now, if you're always cycling through the same kind of silicon samples, then you don't really have to adjust any height there. You just retract to the home position or somewhere like that, and then put a new sample in, and then you can approach again. If you're always changing the height of your sample, you have to be a little more careful, and you just look underneath optically, just with your eye, I guess, and make sure you don't crash into the surface. Our AFM has, again, it has the three legs. You have about 5 millimeters of sample height that you can work with. If you have the motorized stage, you have an additional 5 millimeters, so you have about 10 millimeters of height that you can work with there. Beyond that, we can do things like we can raise the, we can put spacers under the legs and for much higher samples, or we can remove some of the spacers for much thinner samples, I guess, but thinner shouldn't be a problem. The thicker ones might be a problem.
So there's a related question. What is the range of thickness that can be used without any problem?
So within a scan area, so the ZP, the range is about 10 to 12 microns for the flex scanner. In general, you don't want to exceed maybe 50% of that range on a single scan. So a thickness of flake of I would say maybe 2 or 3 microns would probably be probably the max. And in some imaging modes, like in this tapping mode or phase contrast mode, very large Z features aren't very good for. It's not really an AFM sample. It can be done, but it's there are other techniques that are better for that.
Yeah, and I think also this is more on range of the entire thickness of the sample. Like I think. With the use of spacers, we can go much higher.
Yeah, we can go infinite height. Yeah, I mean, we have a tip scanning AFM, so it makes no difference what's underneath it. So a sample could be, not infinite, but yeah, it can be as big as you want it to be.
So we can actually take the scanner and put it on airplane wing if you want, on top of an airplane, and then image the surface there, because it's a trip scanner, and the whole thing, the scanner is completely self-contained.
Yeah.
And if you have further questions, please let us know directly. We can even have a direct conversation with you. If you have a specific sample that you're trying to image, we can work with you and set up a specific demo for you. So yeah, I just want to point out to people who are watching, right? Just look at the image. We've been busy talking, but Ed, you want to comment on the quality that's coming up? And
yeah, I mean, there's some streaks. I mean, the room here isn't as quiet as it needed to be, but it's actually giving us pretty nice the triangles here. We see there's some overlap, and then some of these MOS2 samples it's the second layers growing in the center. We can see here. For kind of a thickness measurement, we can do a little bit of analysis in the software. Let's just take a look what we're seeing. So I'm just going to draw a line here, kind of it's clean line here. And just to get an idea what the thickness are, we'll just look at right before the edge. There's the height, and I'm measuring about 600 picometers for that sample. So this measurement. So on the left side of this triangle and to the right side is a height difference of about 600 picometers. And we can do a little bit better with the with trying to clean it up in post-process. Right now what we're seeing is a sample, the line fit. So we're trying to fit a line through all the data. The raw data actually looks a little bit different just because there's a change in the Z height there. So that's why we use this line fit thing.
Okay, is it possible to AFM for magnetic nanoparticles? Is there an interference from the magnetic sample holder?
I mean, yeah, it's possible to there's two ways of doing it. That's sort of a passive way in which you magnetize the cantilever itself. So you use like cobalt, the cantilever is coated in cobalt or something like that. And you magnetize the cantilever, and then as you pass over it, remember that we're measuring force. And I didn't get into what phase contrast imaging is, but as you pass over a sample and the force changes, you should see a contrast here in the phase. And that's what we're seeing here as we pass over the triangles here. The force changes over it, so there's a change in phase. The same thing will happen for a magnetic particle. It will the magnetic force obviously will change over it. What we could do though is do something what we call a lift mode, in which we, or dual pass, in which on the second scan, we actually go above the sample a certain distance, like a couple nanometers. And then because magnetic and electrical forces are long range compared to surface forces, we should be able to see better contrast on the second pass. Now we also have a variable field magnetic in-plane holder. That means we can apply a magnetic field to the sample to get it to change the poles or get the poles all aligned in the same direction, and then see through MFM how that changes. So those are, two ways of doing it.
Okay. So there is a follow-up. Is there an interference from this magnetic sample holder?
Oh, and this one? No, there isn't. No, because the cantilever I have is non-magnetic. It's just silicon. I mean, nothing in here is. And it's very in the holder, the magnets on the holder are very. I mean, they're not long range. I mean, it's enough to hold the sample down, and in this case, I also clipped it down just to make sure it didn't drift.
Yeah, exactly. So if you worry about magnetic sample holder, we can always use the clip to hold it down. Can we measure biological material derived from cells like exosomes, which are about 100 nanometers in size?
Yeah, absolutely. Yep. Not with this cantilever. I mean, you basically pick the cantilever. You match the stiffness of the cantilever to the material that you're trying to measure. This is a stiff material, so we're measuring a stiff sample. Notice there's some dust or something right in the middle here. It's kind of messing up my image. I'm going to zoom in on maybe this area here. Yeah, but yeah, exosomes definitely. 100 nanometers is definitely in the wheelhouse of an AFM.
Yeah, and also I just want to point out that this setup that Ed is showing, you don't need anything extra. the system.
Yeah.
You don't need to buy a liquid cell or anything else. It just as it comes, you can image in liquids.
Yep.
If a motorized stage is used, can you stitch multiple AFM spots together, images together?
Yes, that's possible. So what you can do is you can do some batch imaging, in which you take an image and you tell the stage to move a certain distance. So the maximum XY scan range is 100 microns. You can tell the stage to then move 90 microns to the left or to the right, and take another image. And then you can go in and try to overlap those images and get a large stitch. And because it's all automated, you can just set it up. You can go home for the night. When you come back, you have 50 images, and then you can stitch them all together and you have one continuous image.
Okay. Should we prefer dynamic mode instead of static mode to perform a topographic measurement?
And I mean, there's some reasons to prefer static mode. Now, static mode will you don't get these like electrical interference effects that might happen in dynamic mode. But what can happen is that you either damage the sample or you can damage your tip, because you're actually making physical contact with the sample. Now, in repulsive mode imaging, you also are making physical contact, but you're not really you're not driving it way as hard as in contact mode. Contact mode is a little easier to do in liquid, but it's also if you have high Z features, it's much easier to use. It's much easier to get in feedback in contact mode than in tapping mode. But in general, you get higher resolution in tapping mode. You preserve the tip in tapping mode. So if you have a sharp tip and you want good XY resolution, you're going to get that better in tapping mode, because you don't blunt the tip. Plus, in tapping mode, you can get the phase contrast image, and then you can do other modes like EFM and KPFM and MFM. That's not available in contact mode.
Okay, so maybe this is a follow-up question. Can we do ECAFM with this setup?
Yes, certainly. We have a special holder for it, which it's made out of PEEK, so you can put whatever your material that you want, your liquid, and then it has feed-throughs for the 3 electrodes that you need. But yeah, you can do that in either tapping mode or in contact mode with an EC cell. Yeah.
Okay, how many measurements can we take in a row without distortion of the image, thermal effects, etc.?
I mean, the drift is certainly a problem for all AFMs. If a system it takes maybe 30 minutes to get to thermally stabilize. So if I place a sample underneath it, in about 30 minutes, the drift is probably as low as it's going to get. If I'm looking for small scan areas, 500 nanometers, we might drift out of the region in a couple hours, two or 3 hours, maybe less, maybe an hour. If we're doing these large scanners, this is a 4 micron. This can do a couple hours at this area without a problem, as soon as it's hit equilibrium.
Okay, so also just addressing the previous question about EFM and specific modes, we are developing specific tutorial videos for each of these modes, and they're coming up on our website. We'll let you know when they come up, and also we will have specific web demos on these modes also. So just keep an eye out for our announcements as they come along. We will have specific modes. Can you explain how the automatic approach works?
Yeah. So I didn't want to close that. We have two ways of doing it. One's a continuous approach, which is our default, and so what it does is that in continuous approach, it just moves the motor that's in the front, applies a speed. In this case, it's 9% of the full speed. And while it's doing that, it's looking at the amplitude signal, and that's what's graphed here. And when the amplitude falls to 50% of what it started at, then it stops the motor. So that's how the automatic approach works. Another way of doing it is a step-by-step approach, in which we move the stage a certain distance, stop, and then bring the piezo and extend the piezo all the way down, and see if we detect the surface. If not, we retract the piezo, the Z piezo, and then we move the stage another step. And I guess they both work well. I think continuous approach is a little faster. But I don't know if that answers your question.
I think it does. If there's a follow-up, please submit the question. Can you explain about tip voltage? I guess this is more about the free vibrating amplitude voltage number, or is it the tip voltage number?
Oh, well, I can talk about both. I mean, tip voltage is your, so we can apply a voltage to the tip. If the tip is coated with it's a conductive, let's say. So if we put platinum on the outside of the tip, we can do two things. We can apply voltage to the tip, and then this phase channel, if we pass over charge on the surface, then it will cause an electrical force. And then in this phase channel, we'll see large contrast as we're passing over those charges. We can also apply tip voltage, and in contact mode, we can measure the current through the tip, through an op amp that's in the scan head. And that way we can get, if the sample's grounded, et cetera, we can measure the conductance of the sample. So if if it's conductive or not, or insulator or conductor, et cetera. Also, tip voltage comes into effect when you're doing KPFM, because that's going to be your feedback mechanisms, tip voltage, but that's done by the controller. This second term, free vibration amplitude, is if I'm away from the surface, far from the surface, this is the amplitude of the signal that we get at the detector. So if you notice this main lock-in, it's like 125, right, millivolts. So it's between 108 and 140 something millivolts. So it's about 125. That's exactly 50% of your free vibration amplitude. So that's what that voltage is.
Okay. What is an appropriate tip for an MFM measurement?
All manufacturers, they'll probably have a section on MFM, or for magnetic force microscopy. It just needs to be coated with a magnetic material. And I think a lot of the time it's cobalt. And every manufacturer has their version, budget sensors or app nano or nano and more, et cetera. They all have their own MFM. So can't be more specific than that.
Yeah, and again, I can expand on this. Like we have a demo schedule for MFM, and also the use of the external magnetic field. So that webinar will go into, or demo will go into more details of this. So please log into that. I think it's scheduled for like 2 or 3 weeks from now. For next question, what is the maximum resolution that we can achieve for the ongoing sample in X, Y, and Z axis?
The Z axis is determined by the noise of the system. And so I just showed you that the noise is below that 600 picometer. The RMS noise is about 40 picometers for the system. Probably rule of thumb, you maybe double that, I guess. So maybe a 1 angstrom. The XY resolution is determined by the radius of the tip. Now this particular tip has a radius about 10 nanometers, let's say, or guaranteed below 10 nanometers. So that's going to be basically determine your XY resolution, maximum XY resolution. And clearly, actually the scan area here is the pixel size is actually bigger than 10 nanometers. So we wouldn't, that tip effect wouldn't come, you wouldn't see it here.
Okay, can charge distribution of a sample can be carried out with this tip and cantilever?
Not this particular cantilever, no.
Yeah, you need a metal coated cantilever.
Exactly.
Yeah, this AFM is possible, but not with this cantilever.
Exactly. Actually, this cantilever, coated cantilevers usually have a little bit larger tip radius than just normal imaging cantilevers. So actually the previous question, you might get the XY resolution might be like 80 nanometers with a conductive cantilever versus less than 10 nanometers for this cantilever.
Okay. So another question, this is more of the samples. In case of samples like a turning insert, is it possible to tilt the sample stage? And what is the maximum tilting angle?
The one I've been using, no, but we can make a sample stage for your sample in which you can tilt, yes. And there's no limit to what you can tilt it to. You can operate the AFM upside down if you needed to. So yeah, because we have a tip scanner, it makes no difference what the sample stage looks like. But this particular one I'm using here is not appropriate for that, I guess.
Yeah, like Ed was mentioning, we did build a system for a customer where the AFM is upside down, looking up. So it's totally feasible. How easy is it to replace the cantilever?
It's quite easy. There are some videos on our website that will show you how to do a cantilever exchange. Because we have these alignment grooves on the cantilever holder, as soon as you place the cantilever on there, the laser will be aligned. So you don't have to really worry about that. In all, it could probably take about 2 minutes maybe to swap out a cantilever. It can be done in a glove box easily, or because the cantilever holder is removable, there's a smaller load lock there that you can also remove it that way if you're worried about that.
How about measurements in fluids?
What's the question?
Yeah, I think answer is can be measured in fluids.
Oh, absolutely, yeah. Nothing extra is needed. You don't need a fluid cell. You can use the same exact holder and same cantilever that I've been using. We can do all this in a drop of liquid.
Okay, there are a couple of questions on STM head for this setup.
Yeah, at the moment we don't have an STM attachment for this scan head at the moment.
And we have a freestanding small STM that
yeah, we do have a freestanding STM, separate unit.
So there is a question, can we have a recording of this? Answer is yes, I was going to come to that. We will have a recording of this webinar. It will be on our website. So hopefully by Monday next week. So those who want to download the webinar and watch it again, free to do that. What is the step size of the approach motor in continuous approach mode of approach?
That has to be measured. It's maybe less than 100 nanometers per step. It really depends more on the speed. So below at the slow speed, you can get below 100 nanometers, I think. I don't know off the top of my head, actually. I shouldn't have been answering that.
Yeah. What mode is better for analyzing bacteria or mammalian cells?
Well, I mean, I guess that goes into the question of how big they are. And I think I was mentioning this before, that in contact mode, it's better for samples with large Z variation, which mammalian cells can be a couple microns in height. Bacteria is probably a little smaller, right? 1 micron maybe in height. So mammalian cells, maybe a lot of time people do it in contact mode, but you can do it in tapping mode also if you have a large enough amplitude with the cantilever. It's hard to do that in liquid to get a large amplitude because there's so much damping of the liquid. So a lot of times people mostly do tapping mode in liquid to image DNA or to image proteins and things like that. But going up to like bacteria, like E. coli or something like that, maybe at the upper limit of tapping mode in liquid. But then beyond that, a lot of people prefer to use contact mode, and you can just use a soft cantilever, one that's less than 1 Newton per meter, or even less than 0.1 Newton per meter, and then you can apply, only 500 piconewtons of force, or even less, and image with that.
So there's a follow-up on that. Is there a basic sample preparation method for protein samples or any biological samples?
Yeah, there. So the proteins, some of the smaller ones are only a couple nanometers in height. So what happens is that a lot of times when you're doing a lot of biological work, you use maybe glass slides and things like that, quartz, to image. And what happens is that quartz is actually, the surface of quartz is actually much rougher than the size of the DNA or the size of the protein. So what you have to do is actually apply the DNA or the protein to a very, very flat surface. And what most people use is either mica or silicon. And there's different ways of preparing a sample with mica or silicon. So the easier one is, suppose mica. Mica is negatively charged. I'll just use DNA as an example. DNA is also negatively charged. Those two things won't necessarily bind to one another. So what you have to do is add a salt or a precursor there that will create a salt bridge between the DNA and the mica. So essentially a really flat piece of mica, some salt to help it bind, and then the purified protein or DNA. Proteins are a little different because it could be either negatively charged or positively charged depending on the pH. So, but a very similar protocol can be established for different proteins too. And I think, Saju, actually, you're more experienced than I am on this, so you can probably.
So I can just extend that. So basically, imaging any biological material or anything for that matter, you want to attach it to a sample, to a surface, and really mica or nice piece of silicon are the substrates of choice. So once you attach them onto it, then there's nothing else to do. You can just image them under liquid. Have it mount the substrate that you have attached to onto this AFM. Add the liquid in there. If you want large quantities of liquid, you can use a petri dish. Glue the sample onto the bottom of a petri dish, and have up to 6 millimeters of liquid. If it cells, it's easier. Just attach them onto a glass slide, and if the glass slide is coated with an ECM, then you can attach a cell easily onto the surface. Bacteria, same thing. If you use something like lysine coated glass slide or something like that, you can attach a sample. So this basically attaching the sample is the tricky part onto a surface at the right concentration. After that, imaging is straightforward. Okay, so another follow-up on this is, can the current setup do live cell imaging?
Yes, with this, with some, yes, it can. The cells won't be alive for long. I mean, what you need to do live cell imaging is is by me a biosample heater to keep the cells nice and happy at 40 C. This currently, what I've been imaging here doesn't have that biosample heater, but it's just a sample holder. If I had the sample holder, I can put it on there, and then we could do the live cell imaging. Yes, no problem.
Yeah, and we do have the live cell imaging setup.
Yeah,
which is an add-on to these existing.
Exactly. It's one of those add-on to because it's so modular. I can just add that to the system.
Can we conduct a webinar session of Fluid FM? Yes, thank you for the request, and we will definitely set up. So for post-processing, what is the best software? We use WSXM for it. Is there any other software better than that?
I have never used that particularly, but what we use is maybe something called Gwydion. It's freely available. It's also, it's open source, and you can use it on Linux, on Mac computers, and on PCs. It does everything, I think. If you want to get a little bit fancier, I would suggest a program called Mountains or Mountains Map. And you can do a lot of kind of pretty images with that system too. But that is a paid software, and Gwydion is free. So
yeah. And WSXM, that company is no longer in business, so they don't, you cannot get updates for that anymore. But if you're using that, you can continue using it. But if you want Gwydion, you can always download it. Or if you need help, just send us an email and we'll send you a link for downloading it. What is the maximum XY scanning area? Are there different interchangeable scanners available for this model?
For this model, it's 100 by 100 microns. And we also sell a version which we call the high resolution version, which is 10 by 10 microns. But it also limits the Z range of that scanner also. So yeah, two versions, 100 by 100 or 10 by 10.
So a question is, can you provide the name spelling of the software you suggested on the screen? I just sent it.
Oh, you did?
You
Okay.
should see it, yeah. Gwyddion. I think I have it right. Okay.
Here, maybe let me, yeah, I'm going to share the screen. So
okay,
I just opened, this is the Gwydion. I just opened this file as I'm doing now. So this is kind of processing you can get out of it. So there's a 3D image, and this is the height image there.
Yeah, so there are quite a few questions on the tip and the tip of the sample. What kind of a tip would you use? I think that can really get into too many details of what kind of tip. It really depends on the type of sample that you use.
We're going to have a video on that too, an upcoming video, right?
Yeah, we are preparing a video on that, on what kind of tips would you use for a particular sample. So hopefully we'll get that out soon. So yeah, I think if there are any more questions that hasn't been answered, oh yeah, it's just tons more. Let's go a few more questions. Are the scanners interchangeable by the user, or should I buy a particular version of the device? Just following on a previous. The scanners are interchangeable, yeah.
Yeah, for the controller can work with a number of different scanners, but the Flex scanner can work in with biological materials, with 2D materials, with everything. So there's no, like for example, we have something called a Flex Bio, and this is the Flex Axiom, but really the scan head itself is the same. So there's no difference between the two units there. It's just more about how the stage is set up, the sample stage. But yeah, the scanners are completely interchangeable with the controller, and it can be used for everything.
For the cameras, the camera that we use, is it a CMOS or a CCD camera?
It's CMOS, I think. Yeah, I think it's CMOS. I'm not sure.
Yeah,
that'll be on our spec sheet.
Is high-speed scanning possible? If so, how many frames per second?
Okay. Yeah, I guess the question is what is considered high speed. So video rate in which you're doing multiple frames per second is not possible. This AFM is a large sample scanner. I guess 100 by 100 microns. Typically, the video rate AFMs are very small sample or small scan range, small sample size. And also, I mean, if you look at it, they're only doing, I don't know, 20 lines per frame. So it's not doing this. I'm doing right here 256 lines right there. So yeah, I mean, it's not a high speed AFM by any means, but it's
larger sample, larger area.
Yeah, large sample, large area. It's a general purpose AFM, benchtop.
Can we overlay an AFM image with an optical image?
Not through our software. But yeah, you'd have to use a third-party software like Mountains. Mountains Map can do that. Yeah, the one I mentioned before.
I think we'll call it a day now. It's been quite a long time. So thanks, Ed. And thank you all for attending. If you have any further questions, please contact us directly. You can send an email to info@nanosurf.com or check on the website. And if you guys have a direct contact at Nanosurf through sales or support, please contact them directly, and we'll be glad to get back to you on that. And also, this webinar will be available on the website within a week. So once again, thank you all, and hope to see you in our next webinar.